All right, the next problem with small populations is demographic stochasticity. Stochasticity just means random changes. So this is fluctuations in population size, age structure, and or sex ratio due to random variations in individual birth and death rates. Some individuals, some years have low births and high deaths by chance. So this is just random variability, but it has to do with random variability inside the population, not from external factors. That's environmental stochasticity. So if a population is small, so for example, less than or equal to 50, there is a chance that low birth rates and high death rates could drop the population size to 0. And we see that here. These are random simulations from just variable birth and death rates for a population. All these populations started with 50 individuals, and they just ran it over and over through time, randomly selecting birth and death rates through time. And you can see that just due to chance, 1, 2, 3, 4, 5, 6 of these populations went extinct in these simulations. Some of them ended up way higher than 50, but some of them completely crashed. Here's an example of demographic stochasticity. The dusky, this is a saltmarsh specialist, the dusky seaside sparrow from South Florida. By chance, the last population had only 5 males. It just so happened that the last 5 offspring were all males, and so they went extinct in 1987. Another part of this is something called the Allee effect. It's density-dependent effects on average fitness if a population gets too small. And so what this basically says is that the population growth rate declines when the population size is smaller. Normally you would expect, if it's due to resources, that when the population is smaller, the population growth rate would go up because there's more resources for everybody. So there's lots and lots of food. But for some very social species in particular, if the population gets too small, they don't do as well because they can't deal with predators or they can't find mates. Flock animals, so this is what they think happened with the passenger pigeons. They think that they used the flocks as a way to protect themselves. And without lots of them, they couldn't protect themselves well enough and predators could get too many of them. And so that's an example of an Allee effect. Another example might be pack animals. So like lions that live in prides or wolves that live in packs. If there get to be populations that are too small, there might not be enough individuals to take down large prey items. So basically, a species needs a certain number of individuals to maintain themselves. So I said again, the passenger pigeon, the Allee effect is thought to be important for them. I said before, they avoided predation by having large groups, so kind of a safety in numbers idea. So they had much lower survival at lower densities. Another part that's probably really important for passenger pigeons is that they're communal breeders. They used to all breed in large trees together. And people actually cut down those trees on purpose to get at the passenger pigeons more easily and to keep them from eating things in their agricultural fields. And so communal breeders is another kind of allele effect. So if you can't breed successfully without a large group, like a communal breeder might need, if your population gets too small, the communal breeding doesn't work and you might not have as successful reproduction. Environmental stochasticity is different from demographic stochasticity. So demographic stochasticity is changes, random chance, related to birth, death rate, age ratios, sex ratios, things like that. Environmental stochasticity is these random variations in the environment that then affect the population. So these might be biotic factors like just random changes in the predator population, the prey population, and competition and disease could be abiotic factors. So like fluctuations in temperatures, droughts, storms coming through, those would all be examples of environmental stochasticity. So an example here, we have the number of adults in black and then total population size in red. There's disease that happens every once in a while in this population, and then by chance there were 3 episodes of disease in a row, and that brought the population down really low. So a final concept is the extinction vortex. And this is the idea that there are so many problems with small populations that you get into these positive feedback loops where when the population gets smaller, it causes one problem with small populations, which makes another problem with small populations more likely, which then exacerbates and makes the population smaller, and so on and so forth until a species goes extinct or a population. So basically, our population gets smaller. You get less genetic variability, means the species is less likely to be able to adapt. When there's lower genetic variation, there might be more inbreeding depression. Then the population might be subdivided by fragmentation, making more demographic variability, so more demographic stochasticity, and all of these lead to a lower population size or a lower number of breeding individuals. You get some environmental stochasticity or catastrophic events. You get some other threats, and before you know it, the population is going extinct. So the extinction vortex is just how some of these problems with small populations exacerbate each other. So when you get smaller populations, less genetic variability, which causes more problems, which may cause the population to be smaller, which may cause environmental stochasticity have a larger effect. You might be more likely to get demographic stochasticity when you have a smaller population, which leads to an even smaller population, and then eventually they're just very vulnerable to extinction. So this is the extinction vortex. And this shows it just in a slightly different way, where you have a small population that loses genetic diversity due to genetic drift and inbreeding. You lose more genetic variability. You reduce individual fitness and population adaptability, getting lower reproduction, higher mortality, smaller population, and then eventually the population just gets stuck and can't recover by any means. So this is the end of the chapter on extinction. I know that was depressing, but we will start talking about fixing this real soon.